Hi, I'm recording this lecture about chapter 17.6, considering many students missed the lecture today, in this week. Right, so chapter 17.6, we're going to talk about this Le Chatelier principle. Right, so this principle is about the shift of chemical equilibrium, and we're going to look at the effect of different reaction conditions and how they change the reaction equilibrium. So for the Le Chatelier principle, right, in chemistry, it states that when you have a chemical equilibrium, right, so you have a reaction that already reached a chemical equilibrium, and if you disturb this equilibrium, it will reattain the equilibrium by undergoing a net reaction. Right? So this net reaction will reduce the effect caused by this disturbance until the equilibrium is reestablished. Right? So basically, it means that you start with an already equilibrated system, and you could either add some products or add some reactants or change the temperature, change the volume or the pressure, right? So to disturb that equilibrium. So what happens after this disturbance is that there will be some chemical reaction going on that will reduce the dispersions, right? So until this new equilibrium is reached. So this net reaction happen in between, right? Between the initial equilibrium and the final equilibrium is called a net reaction, right? So this net reaction because is shifted to the right, right? So if this net reaction generate more products, we'll say this net reaction, right, is shifted to the right, or we said the equilibrium has been moved to the right, right, toward the side of the product. If this net reaction generates more reactant, we say there's a shift to the left, or the equilibrium has been shifted to the left-hand side. Right, so this disturbance of the equilibrium can be caused by three factors. So a change in concentration, a change in pressure, and a change in volume. For the second one, for the change in pressure, it can be also caused by a change in volume, right? So because the ideal gas law tells us that PV equal nRT, so P and V has an inverse relationship, right? So increasing the pressure meaning that you're decreasing the volume, or increasing the volume meaning that you're decreasing the pressure. First, let's take a look at the effect of a change in concentration. So when a system is at equilibrium, right, and you try to disturb this equilibrium by adding one of the reactant or the product, right? So by changing its concentration, this net reaction, it will react in the direction that reduces this change of concentration. For example, if you add some reactant, right, this net reaction will reduce the increase of this reactant by reacting that reactant into products. Right, so if you add more products into the equilibrium system, right, the net reaction will react more products into the reactant, right? So the tendency is to reduce the change of concentration, right? If you increase the concentration of something, this net reaction will reduce that increase by reacting it or consuming it. Right, so similarly, if you decrease the concentration of the reactant, right, so this net reaction will go against it, so the net reaction will increase the amount of the reactant. So that is done by reacting more product into the reactant, right? So on the other side, if you decrease the amount of the product, right, that means you have more reactant will react and generate into product, right? So to reduce the decrease of the concentration of the product. Right, so in this example, let's take a look at this chemical reaction. Right, so we have this gas molecule PCl3 reacting with this chlorine gas Cl2 and generating this PCl5 gas. Right, so using the reaction quotient, right, we can represent this QC, right, is equal to the concentration of product divided by the concentration terms of the reactant. And here, because the coefficients are all equal to 1, so all the exponent is equal to 1, so we don't need to write them. Right, let's say this reaction right now is at equilibrium. Right, so at equilibrium, QC is equal to Kc. And for this chemical reaction at this certain temperature, this Kc value is equal to 24. Right, so first let's see what's gonna happen. Right, so what's gonna happen, say, if we increase the amount of this product. Right, so if we increase the amount of this product, right, this net reaction is gonna reduce that increase of this PCl5. Right, so that means this PCl5 increase, some of it is gonna be reacted back into this PCl3 and the Cl2. Right, so that means this reaction is gonna be shifted to the left. Right, so as indicated here. Right, so if we increase the amount of PCl5, right, so the amount increase will be reacted right into this reactant. So this reaction is shifted to the left, or we say this net reaction, right, has a direction to the left. Right, so if we decrease the amount of the reactants, we will have the similar shift. Right, if we decrease the amount of these two reactants, right, so the net reaction will generate more of this reactant, right, to go against that decrease. So the chemical reaction will be shifted to the left. So on the opposite end, right, if we decrease the product, right, decrease the amount of the PCl5, this net reaction will generate more of this PCl5, right? That is done by reacting more these reactants. So in that case, the chemical reaction will be shifted to the right. And notice that when we represent this QC and the KC, right, so only the gas or the aqueous phase is involved, right, in this expression. Remember, for solid and liquid, their activity is equal to 1, right? So we don't write down solid and the pure liquid in this expression. So that means, well, no matter how we change the concentration of the solid or the pure liquid phase, right? No matter how we change the amount of it, because it's not showing up in this calculation, it won't affect the chemical equilibrium. So now let's take a look at this example. Right, so we can predict the effect of a change in concentration on this equilibrium position, well, meaning that which direction this equilibrium is shifted. Right, so we have a chemical reaction. So we have hydrogen sulfide, right? So that is the very bad smell come from the rotten egg, reacting with oxygen to generate sulfur and water. Right, so notice the physical state. We have gas and the gas, solid here, and this gas, solid sulfur, and the gas phase water. Right, so it asks us that what happens to the concentration of water, right, if oxygen is added, right? So what happens to the concentration of water when this oxygen concentration is increased? Right, so based on what we learned in the previous slide, right? So if we increase the amount of oxygen, right, that means the net reaction will go against it, right? So the net reaction will consume of this oxygen. So the reaction will proceed to the right, right? So when the net reaction proceeds to the right, it will generate more of this water molecules, right? So this concentration of water will increase. Right, so now we know that the water concentration is gonna increase. Right, so let me erase this for the next. Right, so for B, it says what happens to the concentration of hydrogen sulfide, one of our reactants, when the oxygen concentration is increased. right? So similar to the previous one, right? So when we increase the concentration of oxygen, the net reaction, right, will go against it, so it's gonna consume oxygen. The oxygen is consumed by reacting with hydrogen sulfide, right? So when you consume oxygen, hydrogen sulfide is also being consumed, right? So for hydrogen sulfide, its concentration is gonna decrease. For C, it asks us that what happens to the concentration of oxygen if this hydrogen sulfide is removed. Right, so we want to see that if the concentration of this hydrogen sulfide becomes zero, right? So meaning that the concentration go down to zero, what happens to the concentration of oxygen? Right. So in this case, because the decrease of hydrogen sulfide, right? So the net reaction will generate some of it, right? Because it go against it, right? So that is achieved by reacting the sulfur and the water, right, to the left, right? So that will generate more hydrogen sulfide, but at the same time, you're also generating oxygen, right? So the oxygen concentration is gonna increase. Right? So we say the concentration of oxygen is gonna increase. So for the last one, it asks us that what happens to the hydrogen sulfide concentration if the sulfur is added. Right, so sulfur here, notice its physical state is a solid, and as we talked about in the previous slide, that because it's solid, right, that does not appear in the expression of a Q or C, right? So meaning that it has no effect on the equilibrium. So it has no effect on the concentration of the other components in this chemical reaction, right? So we say the hydrogen sulfide is unchanged. Right, so in this slide, we'll demonstrate a experimental data, right? So a set of experimental data on the same chemical reaction, right? On this same chemical reaction. So we have the same chemical reaction, and the initial condition is already at equilibrium, right? So this is the equilibrium concentration, right? Which is the initial equilibrium condition. Right, so say now we have a Kc value here, right? So this Kc value is equal to 24, right? Which is calculated by these three equilibrium concentrations. Right, so now we adding some Cl2, which is the reactant, right? So we're trying to disturb this equilibrium by adding Cl2, and by this much. Right, so after we add this Cl2, right? So the concentration of Cl2 increased from 0.125 to 0.2, right? So the at the beginning, right? So at the beginning, the concentration of the other reactant and the product doesn't change. But due to this disturbance, we know that there's gonna be a net reaction going on, right? So and we know the direction of it because we're adding the reactant, right? So the net reaction is gonna proceed to the right. So you will generate some more product, right, by consuming some of the reactants, right? So for the reactant, we have minus X to represent the change of this concentration, and for the product, we have positive X. And so this is the concentration at the new equilibrium, which is equal to 0.2 minus X, right? For chlorine is also equal to 0.2 minus X, right? 0.2 is the new initial value, right? For the product, it's going to be 0.6 plus X. Right, so here we can calculate X, right? Because we are staying at the same temperature, right? So the equilibrium doesn't change, right? So using this quadratic formula, we can calculate X. or from the experiment, right, we can actually measure the concentration of this new equilibrium concentration, right? So if from this plot on the right, we can see that before this first dashed line, this vertical dashed line, the concentration of the product and the reactant, right, is constant, right? So at the moment of this disturbance, right, which is caused by the increase of this chlorine concentration, right, we can see the reaction, the reaction is no longer at equilibrium. So the Q is no longer equal to K. So for the products, right, we said the concentration is going to increase by X. And for the reactant, the concentration is going to decrease. And is changing until the new equilibrium is reached, right, which is represented by the second dashed line. So after the second dashed line, the concentration remains constant again. And so this corresponding concentration is the new concentration for each reactant and the product. Right, so by calculating X, or from the experimental data, we said X is equal to 0.037. Right, so you can see at the original condition, right, we have this concentration, equilibrium concentrations, and at the new equilibrium, we have this new concentrations. But no matter initial concentration or the final new concentration, the equilibrium constant doesn't change, right? So it's still equal to 24. Why? Because the temperature remains constant, right? So only temperature can change. Only the change of temperature can change the value for the equilibrium constant, right? So the equilibrium constant in this case remains as 24. So next, let's take a look at the effect of a change in pressure. Right. So as I mentioned earlier, a change in pressure also means a change in volume, right? Due to this inverse relationship between pressure and volume, right? So if you compress something, you decrease the volume. That is done by increasing the pressure, right? So this effect of a change in pressure or volume, right, is very obvious for chemical reaction involve a gas, right? So it has negligible effect for a chemical reaction involve only solid or pure liquid or aqueous phase, right? Because for the same amount of a substance, the gas phase occupies the largest volume, right? So there's a change of pressure will change the volume significantly because gas is more compressible than the solid and the liquid. Right, so let's take a look at this example. Right, so we have three reaction conditions. Right, so first let's take a look at the one in the middle. Right, so this figure here demonstrates the equilibrium condition. Right, so again we're using this chemical reaction. Right, so at equilibrium, right, so we have this gas molecules in this container, and on top we have a piston, right? So the advantage of using a piston is that we can actually control the volume, right, by pressing it or lifting it, right? So for this chemical reaction, right, we have for the reactant we have 2 moles of gas. Where does the 2 come from? Look at the coefficient, right? Because we have 1 mole of PCl3 and 1 mole of Cl2, right? So the total 1 plus 1 is equal to 2, right? And for the products, we only have 1 mole of PCl5, and this reaction is already balanced, right? Meaning that for every 2 moles of the reactants, we generate 1 mole of the product. Right, so QC is expressed at this way. Right, so first, say if we want to increase the pressure, right? So we press this piston, right? So we press this piston. So what the system doing is that it is compressing these gas molecules, right? So the pressure has been increased, and because this piston has moved down, the volume available for these gas molecules becomes smaller, right? So higher pressure right, is accompanied by a lower volume. So when this volume become lower, this gas molecule is gonna feel more crowded, right? So this equilibrium then is shift, right, to form fewer molecules of gas because you have a less space available for these molecules, and these gas molecules don't want to be so crowded, right? So they want to a decrease in the number of molecules. So this chemical reaction will be shift to the direction that has less number of gas molecules. In this case, we have less, right? We have lower coefficient on the right hand side. So this chemical reaction will shift to the right, right? So it will shift to the right when P is increased, right? So when we increase the P, the chemical reaction will shift to the right, because by shifting the chemical reaction to the right, we have a less number of molecules, right? Which is suitable for a smaller volume. Right, so if we lower the pressure, right, by lifting the piston, right, so by lifting it, we are increasing the volume for these gas molecules. Right now, for these gas molecules, they have more space, right? So the equilibrium is going to be shifted to form more of the molecules, right? Because they feel so lonely, they want more friends, right? So they want to the reaction will generate more molecules, right? So in this case, if we let me use another color, right? So if we decrease the pressure, right, so the reaction will be shifted to the left, right? Because on the left hand side we have more molecules, right? So that's the case for this chemical reaction, okay? And if you do not understand this this chemical shift, so let's use this analogy, right? So for example, say if you live in a condo, right, which only has 2 rooms, so you probably only have maybe 5 or 6 pieces of furniture, right? Because you only have that much of space available, right? But say if you moved to a big house, right, that has 5 or 6 rooms, you need more furniture to fill those empty rooms, right? So if we check this reaction volume, right, as it is size of the house and the number of gas molecules at the number of furnitures, right? So you're gonna understand this relationship, right? So a bigger house, more furnitures, right? So a bigger volume, that meaning more gas molecules. So for the effect of a change in pressure or volume, right? So in order to have an effect, we must have a different number of moles or different number of gas molecules on the left hand and the right hand side, right? Meaning that the number of the coefficient for the gas phase should be different, right? Here I'm talking about the total of the coefficient, right? So in this case, same chemical reaction, we have 1 here, that's a 2, and the 1 here, so we have 2 on the left hand side, 1 on the right hand side. Right, so if you have a more complicated chemical reaction, it involves different physical states, right? So we're counting this coefficient only for those gas phase molecules, not the solid or liquid or the aqueous phase. Right, so in this case, where when we have a different number of gas molecules or number of moles, so the change of pressure or change in volume will have an impact on the position of the equilibrium. Right, so we also have chemical reactions that have the same number of moles of gas, right, for the reactants and products. Right, for example, here we have 1 mole of hydrogen, 1 mole of iodine, so the total is 2 mole. Here we have 2 moles of hydrogen iodide, we also have 2 moles, right? So in this case, because the number of moles of the gas are the same, right, for the reactants and the products, we said the change in volume has no effect, right? It has no effect on the equilibrium for this chemical reaction. And again, as long as the temperature is not changed, right? So if you change the volume or change the pressure, but not change the temperature, this Kc value still remain constant. So now let's look at example on predicting the effect of changing volume or pressure on the equilibrium position. Right, so the question asks, how would you change the volume of each of the following reactions to increase the yield of the products? Right, so we want to increase the yield of all these products. Right, so now let's take a look at this chemical reaction A. We have a solid, right, so generating another solid and a gas. Okay, so a gas is involved and is on the right hand side. Right, because the question said we want to increase the yield of products, right? So we want to increase the concentration of CO2, right? So CO2 is a gas phase, right? It requires more space, more volume, right? So to enhance its yield, we need to increase the volume, right? So we want the chemical reaction to be shifted to the right hand side, right? So that way, the yield of carbon dioxide will be increased. So we want to increase the volume. So for the second chemical reaction, we have a solid reacting with a gas and generating another gas. So for the reactant, the gas phase molecule has 3 moles, right? So has a coefficient of 3, and for the products, it's only 1, right? So the number decreases from the reactant to the products. Right, so if we want to increase the concentration of the product, right, which has a lower coefficient, right, so that means lower the number of molecules, right? So if we want to increase the formation of this product, we should decrease the volume, right? So by decreasing the volume, the reaction will proceed or be shifted to the right hand side, so generating more of this SF6. So for the last one, we have a chlorine gas reacting with 1 mole of iodine gas and generating 2 moles of this ICl, right? So iodine chloride. So we have a 1 mole here, 1 mole here, so the total is 2. We have a 2 here, so we have equal number of moles of the reactants and the products in gas phase. Therefore, a change in volume has no effect, right, on this concentration or on the yield of the product. Last, let's take a look at the effect of change in temperature on the chemical equilibrium. Right, so before I do that, let's quickly record the concept of enthalpy of reaction and also isothermic and endothermic reaction. I say we have a chemical reaction AB give you C and D, right? So it's a reversible reaction. So for any chemical reaction, the delta H of enthalpy, right? So delta H of the reaction, which means the change of energy, right? So that's equal to the total energy of your products minus the total energy of your reactants. Right? So it's products minus reactants. Right? So if your delta H of the reaction is less than 0, right, meaning that when your product is smaller, the energy of product is smaller than the energy of the reactant, right? So which give you a negative value, right? So delta H will be smaller than 0, right? We call it isothermic reaction, right? So it's isothermic reaction, meaning that energy is being released, right? So we write energy or heat, right, on the same side of the products. Right? For if you have a delta H greater than 0, that reaction is an endothermic reaction, right? Meaning that the energy is required for the reactant and to react into products, right? So we write down the energy on the same side of the reactant. So to determine the effect of a change in temperature, a good way to do so is treat the temperature, right? Treat temperature as energy, right? So higher the temperature, the higher the energy. And so for a chemical reaction, you can consider this energy, right, as a component of this equilibrium system, or just treat it as a reactant or a product, right? Treat it as a constant. And the amount of energy is the concentration, right? So for example, if I have a high temperature, that means I have a high energy, right? So if I consider energy as a component, right, in this equilibrium, that means the energy has a high concentration, right? So to determine the effect of this energy, you can use the same way as you use to determine the effect for the concentration, right? For example, if I increase the temperature for an isothermal reaction, right? So for this isothermal reaction, I increase the energy, right? So by increasing temperature, meaning increase the energy, right? So because the energy is on the side of the products, right? So the net reaction is gonna reduce it. So the chemical reaction will be shifted to the left, right? To the side of the reactant, right? So again, treat this energy as a another product, right? Because on the side of product, you can treat it as another product, right? If you increase the temperature, you increase its amount, right? So you increase the concentration of this energy product, right? So that will shift the chemical reaction to the left, right? So we can say a temperature rise, so increase in temperature, right? So will decrease the equilibrium constant for a system with a negative delta H, right? So a negative delta H means it is a isothermic reaction, right? So it is a isothermic reaction. So like this case, right? For isothermic reaction, the chemical reaction shifted to the left, meaning that you have more product, more energy, more reactant generated. Sorry, you have more reactant generated, right? And more C and D consumed, right? So if because K is equal to, right, K is equal to the C and D divided by A and B in this case, right? So a shift to the left, meaning that you consume more C and D and increasing the concentration of A and B. So you are decreasing the numerator and increasing the denominator. So the K value is gonna decrease, right? So the K is gonna decrease. For a endothermic reaction, right? So let me use another color. So for endothermic reaction, the delta H is greater than 0, right? So the energy is required. So you can treat this required energy, right, as a reactant. So if you increase the temperature, you're increasing the concentration of this energy, right? So that means the chemical reaction will be shifted to the right, to the side of the product when you're increasing the energy. So that will increase the amount of C and D and decreasing the amount of A and B, right? So we said that for a increasing temperature, right, will increase the equilibrium constant, the Kc value, for a system with a positive delta H of the reaction, which is a endothermic reaction. Right, it's kind of hard to write with a mouse, right? So, right, for endothermic reaction, right, so we increasing energy because energy is on the side of the reactant, that will generate more product, right? So your K, the numerator is going to increase, the denominator is going to decrease, so you have a higher Kc value. Right, so as we mentioned earlier, right, so among all the three changes which could affect the equilibrium position of the chemical reaction, only a change in temperature affects the value of K, right, affect the value of equilibrium constant. A change in concentration and change in volume do not. Right, so for the same chemical reaction we've been looking at, right, so based on this sign of this delta H is negative, right, it's less than 0, so we know it is a isothermal reaction. Right, so for isothermal reaction, right, so that means if we want the reaction to proceed to the right, right, so we will add energy on this side, right, on the side of the product, right, so let me use Q to represent this heat or the energy. Right, for this reaction, if we want to generate more of this product, right, so that means we need to decrease the amount of the heat, right, so that is done by lowering the temperature. Right, if we want to increase the amount of this PCl3 and Cl2, right, so that's the reverse of this direction, right, so we want to increase the amount of Q, right, so by increasing the energy. So let's take a look at this practice problem, right, so it's predicting the effect of a change in temperature on the equilibrium position. And so the question asks, how does an increase, right? So how does an increase in temperature affect the equilibrium concentration of the underlying substance and the K value for each of the following reactions? Right, so first let's figure out the change of K, right? So because in the previous slides we learned that, right, so for a isothermal reaction, right, for isothermal reaction, if we increase the temperature, right, so let me try again. So if we increase the temperature, that will decrease the Kc value, right? That will decrease the equilibrium constant. Right, for an endothermal reaction, it is the opposite, right? If we increase the temperature, the K value is also gonna increase. Right, so just by looking at the sign of this delta H, right? So this one is a isothermal reaction, right? So increasing the temperature will decrease the K value. Right, so this one's endo, so is the third one. Right, so for both of them, increasing the temperature, right? Because the increasing the temperature is a condition in this problem, so the K value is gonna increase. Right, now let's take a look at the effect of the concentration for this underlying substance. Right, so now let me erase this. Right, so first the underlying substance is the product, and we know this is an isothermal reaction, right, meaning this Q is on this side of the product. Right, increasing the Q value, meaning that the reaction is gonna be shifted, right, left or right. Take a couple of seconds to think about it. Right, so because it's an isothermal reaction, right, the Q is on the right hand side, right, so increasing the temperature, right, is not favored for this forward reaction, right, so it's actually favored by this reverse reaction, right, so by increasing the amount of heat, the reaction is going to be shifted to the left, right, so that the left shift meaning consume some of this CaOH2, which is calcium hydroxide, right, so you're going to consume some of the product due to the shift to the left, right, so we say the concentration of CaOH2 will decrease, right, so earlier we determined the K will also decrease. Right, so let me erase this. Right, for the second reaction, the underlying substance is carbon dioxide. Right, so but in this case we have positive delta H, so the Q is on the left hand side of the reaction. Right, so Q is the reactant, the heat is the reactant. right? So increasing temperature meaning increasing this Q, right? So the reaction is gonna forward or be shifted to the right hand side, right, to the side of the products. So we're increasing the amount of CO2 formed, right? Again, right, because this Q is on the left hand side, it's an endothermic reaction. So increasing the temperature increase the amount of energy, so which is preferred, right, by this forward reaction. So the reaction is gonna be shifted to the right, right? So we're gonna generate more products, right? So the CO2 concentration will be increasing. And earlier we determined the K will also increase. For the third reaction, right, so the underlying substance is sulfur dioxide SO2, right, so it is a reactant, and the delta H is also positive, right, so we put Q on the left hand side, right, so by increasing the temperature, right, same as the second equation, we are moving the equilibrium to the right, right? We will shift it to the right. So more of the sulfur dioxide will be consumed. So the concentration of sulfur dioxide will decrease, but K will increase, right? As we determined earlier. So we say sulfur dioxide will decrease, right? But K value will increase. Because the equilibrium constant is a factor of temperature, right? So we can actually use this two-point version of one-half equation to calculate the equilibrium constant at another temperature, right? If we know this equilibrium constant at a known temperature and the delta H of the reaction, right? So the format of this reaction is very familiar, right? So earlier when we look at the partial pressure, right? So we have this two-point version of this Clausius-Clapeyron equation, right? So when we look at the chemical reaction rate, we have this two-point version of this Arrhenius equation, right? So this one-half equation is very similar to those previous two equations we learned before, right? So here the K is the equilibrium constant, and we have a delta H of the reaction, right? So T1, T2 is a different temperature. So in this equation, say if we know the rate constant, the equilibrium constant K1 at temperature T1, and if we know the delta H of the reaction, we can figure out the K2 at any T2, right? So we can figure out the equilibrium constant at any other temperature. Here R again is the universal gas constant, which is equal to 8.314 joule per mole and Kelvin. So I have 4 homework problems for you guys, right? So this will be similar to what we did in this practice problems, right? Figure out the direction, right? The change of this chemical equilibrium, right? So which direction this net reaction is shifted, right? So and make sure you work on this because you're gonna expect a lot of those problems on our third exam. And after this slides, I prepare some example problems, right? So your third exam will contain some problems very similar to this, right? So first, let's see, we have this chemical reaction, right? So we have 2 moles of gas generating 1 mole of gas and 3 moles of another gas. So on the side of the right hand, we have a total of 2 moles. But for the right hand side, we have 1 plus 3, so that's a total of 4 moles. Right, so this is a test. This is a test on your understanding of how does the change of volume affect the equilibrium precision of a chemical reaction. Right, so the question asks, predict the effect of increasing the container volume on the amount of the reactant and the products. Right, so if we increase the volume, right? So based on what we learned, it is preferred more molecules, right? More molecules is preferred, and because we have a higher number of coefficients on the right hand side, so this increasing volume, meaning that the reaction is gonna be shifted to the right hand side, right? To the side with more gas molecules. So we said the concentration of the reactants is gonna decrease, and the concentration of the product is gonna increase. So the correct answer is A. This problem, we have this chemical reaction, and it tells you it's a isothermal reaction. Right, so the question asks you, what happens if we increase the temperature? Right, so when the temperature is raised. Right, so actually you can solve this problem using two approaches. Right, so first we can use the direction of net reaction. Right, so because the Q is on the right hand side, right, this is the isothermal reaction. So the Q is on the right hand side. So if we increase the temperature, that meaning we're increasing the amount of energy, right, on the side of the product, right? So that will make the shift to the left, right? So that will generate more of the reactant, right? So NO, so the concentration of NO is increasing, right? So what's the relationship between concentration and the partial pressure, right? So remember, the partial pressure of a gas is equal to the total pressure times this term called the mole fraction, right? So this XA is mole fraction. The mole fraction, right? So the mole fraction is equal to the number of moles for this gas molecule A divided by the total number of moles for all the gases. Right, so this is the total. Right, so the higher the concentration, right, that means the more number moles of this gas molecule A, so that will give you a higher partial pressure. So in this case, because this chemical reaction shifted to the left, we're generating more NO. So more NO means a higher mole of NO. So this higher mole fraction means higher partial pressure. Right, so the answer should be C. Right, so the partial pressure of NO will increase. Another way to solve this problem is using the concept that for an isothermal reaction, right? So remember, for isothermal reaction, increasing the temperature will decrease the equilibrium constant, right? Because the equilibrium constant is equal to the concentration terms of the products divided by the reactants, right? So to decrease the K value, we need less product and more reactant, right? So we're increasing the concentration of the reactant, right? So you will end up with the same result, right? So C is the correct answer. So for this problem, we have a endothermal reaction, right? Why? Because it's a positive number, right? So it's greater than 0, so it's an endothermal reaction, right? So I will put the Q on this side, right? So I will put Q on the left hand side, and it asks us that under which conditions would you expect to produce the largest amount of the oxygen? Oxygen is the product, right? So we want the chemical reaction to shift to the right hand side because that's the direction of oxygen, right? So we want to increase the amount of oxygen, right, by changing the temperature or the pressure, right? So by looking at this choices, is a combination of a change of temperature and the pressure, right? So first, let's look at the effect of temperature, right? So because it's endothermal reaction, the Q is on the left hand side, right? So to shift the chemical reaction to the right, we want to increase the amount of heat, right? So we want to increase the temperature, right? Because increasing the temperature increase the amount of heat, right? That will shift the chemical reaction to the right. So we want a higher temperature, so that's between A and C, right? So Another way to do this, again, an increase in temperature, right, meaning that K is also increasing, right? So because K is the product over reactant, right? So that means you want to increase the product and decrease the reactant, and that is achieved, right, by increasing the K value. Because it's an endothermic reaction, we need an increase in temperature, right? So we want high temperature. So how about the effect of pressure? So pressure, remember PV equal nRT, right? So the inverse relationship. So high pressure meaning low volume, right? So low pressure means high volume, right? So in between A and C, high pressure, right, in A also means a lower volume, right? So in C, lower pressure also means higher volume. So let's look at the sum of the coefficients for these gas molecules. Right, so on the left hand side you have 2, on the right hand side you have 2 plus 1, which is 3. Right, so we want more oxygen, so more products. So we want the reaction proceed to the right hand side, because the right hand side has a higher number of these coefficients, the sum of the coefficients. Right, so we want a higher volume. So a higher volume meaning low pressure, right? So the correct answer should be C. So for the last problem, we're looking at this chemical reaction. We have sodium hydroxide solid absorbing the carbon dioxide gas and forming this sodium bicarbonate, or it's also called sodium hydrogen carbonate. It's delta H less than 0, meaning that it's an isothermic reaction. Right, so isothermic reaction, the Q is on the right hand side. So the question asks which of the following action will decrease the concentration of CO2. Right, so we want the CO2 concentration to decrease. We want it to be consumed, right, meaning that this net reaction should be shifted to the right. Right, so for an isothermic reaction, if you want the chemical reaction to shift to the right, we want to lower the temperature. Right, so the answer should be D, right, lowering the temperature. So let's use a case study, right, to better understand this Le Chatelier principle and its application in the synthesis of ammonia. Right, so the synthesis of ammonia can be checked more than 100 years ago, right, back to 1913. A German scientist, his last name is Haber, so we also call this process a Haber process. Right, so in this process, the ammonia is produced by reacting 1 mole of nitrogen gas and 3 mole of hydrogen gas, generating 2 moles of ammonia. And this is an isothermic reaction, right, because this delta H less than 0. So we can put the Q on the right hand side. Right, so ammonia has been widely used, right, in the making of fertilizers. And right now we're making, the whole world's making about over 110 million tons of ammonia every year. So so my question for you guys is that, say if you are the manufacturer, right, so if you are the chemical engineer in the industry for making ammonia, what will you do to enhance the percent yield or enhance the formation of this ammonia? Right, so think about what we just learned in this chapter, right? So because we've tried to shift this chemical reaction to the right, right? So based on the information provided, right, in this chemical reaction, what will you do to enhance the formation of ammonia? Right, so pause the video for a couple minutes and think about it. Right, in terms of the concentration, the volume or pressure, and the temperature. Right, so first, let's consider it from the perspective of a change of concentration. So if we want to enhance the formation of ammonia, first what we can do is remove ammonia or take it away as it forms, right? So if we lower the concentration of ammonia, right, the reaction will be shifted to the right. Right, so that's the based on the change of concentration. Right, so removing the ammonia will enhance its formation, right? Because that will shift the chemical reaction to the right. So how about the effect of volume? Right, so let's look at the number of coefficients. Right, we have a total 4 moles on the left-hand side, 2 moles on the right-hand side. Right, so to enhance the formation of ammonia, which has a lower number of coefficients, we want to decrease the volume. Right, so we want to decrease the volume, so the reaction is shifted to the right. And how about the temperature? Right, so we know it's a isothermal reaction. Right, so we want to lower the temperature, so the chemical reaction is shifted to the right. So let me erase this. Right, so we want to lower the temperature. Right, so the reaction is shifted to the right. So now we know what shall we do, right, to enhance its percent yield or enhance the formation of it. But if you are the chemical engineer on site and you came up with these 3 strategies, you're gonna ask yourself, can I achieve these 3 conditions? If not, what's preventing me from doing so? And so first, think about remove it as it forms. Can I do it? Yeah, I think that can be easily done, right? Because if you compare this, the boiling point of these 3 gases, right, ammonia has the highest boiling point, meaning that if you cool it down, right, if you cool the whole mixture containing these 3 gases, ammonia will be the first one to condensate, right? It will be the first one to become a liquid phase. So if ammonia become liquid phase and the nitrogen and the hydrogen remain as gas phase, you can pump this ammonia away from the gas phase, right? So that can be achieved, right, pretty easily by controlling the temperature in this mixture, right? By lowering temperature, you can remove the ammonia from the other 2 gases, so that equilibrium will be shifted to the right. But how about the other 2, right? So decreasing volume. Remember, decreasing volume means increasing the pressure, right? So can we decrease the volume as small as we want? No, right? If we do so, we'll increase the pressure tremendously, and the higher pressure means it's not safe, right? So you don't want a reaction chamber that has such a high pressure. It's not safe. Safety should always come first, right? So you have to find this optimum reaction volume or pressure, right? So it is preferred by the reaction, but also our reaction chamber can hold the high pressure. How about the temperature? We want to decrease the temperature so the percent yield can be increased, or the ammonia formation is preferred. But thinking about what's gonna happen if we decrease the temperature. Think about what we learned in chapter 16. You got it? Chapter 16, we talk about the rate of a chemical reaction, and we said if we decrease the temperature, the reaction rate is also gonna increase. So although decreasing temperature prefer the formation of ammonia, but this reaction is gonna happen so slow, right? So do you want to operate a manufacturer plant that everything acting so slow? No, because longer time meaning more cost, right? So you want to compromise this high and low temperature. First, you want it to react fast, right? So less time means less money, right? So also you want the reaction to prefer the formation of ammonia. So you have to find this optimum temperature. So in the figure here, the little circle here give you the industrial condition for manufacturing this ammonia gas. And as you can see, right, the temperature is almost 400 Celsius. It's not the low temperature that we desired. And that's because we want to increase the reaction rate, right? So that is achieved by sacrificing the percent yield. And also in terms of the pressure, right, it is done around 200 atm. So at room condition, right? So on the surface, ground surface, we have 1 atm. So that's already 200 times the atmosphere pressure. So at this condition, we have about 40% yield, right? Meaning that for every 100 moles of the reactant, only 40 moles of the ammonia will be formed, right? So actually, that's the best we can do right now, right? You can say, oh, why don't we decrease the temperature? And if you decrease the temperature again, the reaction can be so slow. Or why don't we increase the pressure, right? So if we increase the pressure here, like 1000 atm, right, at 200 Celsius, is almost 100% yield. But first, we can barely achieve that high temperature, right? So our reaction chamber cannot hold that high temperature, the pressure. And then also we want the reaction to react fast. So on this table here, you see the effect of a temperature on this equilibrium constant. Right, so the lower the temperature, the higher the equilibrium constant. Right, so if you increase temperature, you can see the equilibrium constant decrease, right, significantly. So the figure below here gave you the flow diagram of this whole manufacture process. Right, so at the beginning we have a mixture of the reactants. So hydrogen and ammonia follow the ratio of 3 to 1, which is the coefficient in the chemical reaction, right? So that's recommended by the stoichiometry. So first we pump this air reactant into the compressor, right? So we compress the molecules, right? So we decrease the volume or increase the pressure, right? So that's what we want, right? So because that will increase the percent yield of ammonia. And then we add this compressed gas into this reaction chamber. So in this reaction chamber, we have some catalyst, right? So for this reaction, a good catalyst will be iron-containing minerals, also some metal oxides, right? So that will speed up this chemical reaction. So in this mixture here, we have this equilibrium condition where you have ammonia, hydrogen, and nitrogen, right? So then we can condense this ammonia, right? So that meaning we want to decrease the concentration of ammonia, which is our strategy number 1, right? So we take it away as it forms. And how do we do so? We decrease the temperature, right, for this mixture, right? So the ammonia will condense first, and the nitrogen and hydrogen will remain as gas phase. And we're not wasting those, right? Because those are the reactants. So we pump those gas back into the original compressor. So join the next reaction. So the reactant is not wasted. Right, so this condensed ammonia is in the liquid phase, right? So we can fill this ammonia into storage tank. Alright, so that's everything we're gonna cover in chapter 17.6. And please comment and like the video, right? And also, if you have questions, you can either email me or put your question in the comment, and I will get back to you as soon as possible. And also, let me know how do you like this format of teaching, this online lecture. Right? If you like it, we can continue doing this for the rest of the semester or until this coronavirus thing has go away.